which you consider all the operational expenditure. So we do have a application on specific markets where we are highly competitive, not only on the grid pricing or against the grid pricing, but also if you look on an outlook forward, we can warrant more or less, assuming we have wind, a flat pricing on the electricity. So these are two major driving forces for us to be in the market. So the two portfolio we are marketing actively on the markets are on the left side, the turbine we call the O design, some would say the original design, based on the Ørsted turbine from 1988. And on the left side, we have the T design. Some call it also the Land Rover. In principle, they are almost equal. We use the same installation and services principle. We use the same building parts, the same components. The major difference is the O design on the left side was born with a 14-meter rotor. It's an IEC wind class 3, and it has actually a 2-generator solution with the design philosophy to support also production in low wind scenarios. The turbine on the right side is a IEC wind class 2, and it was born with a 16-meter rotor. We later on actually updated the O design for specific markets with a 60-meter rotor as well. They are both applicable for a conical tower structure, and we deliver them in various tower heights, such as 15, 17, and 18 meters, which are all related to national requirements or opportunities. The turbine on the right side is also available on a fixed tower, lattice tower, 22 meters. We tend to focus on the T design when it comes to new market introduction, but both turbine portfolios are available for the markets. Throughout the time, we have had opportunities, and mainly driven by national requirements and also national feed-in schemes, to adjust the output power or the nominal power of the turbines. So the turbines are seen and available in the past on various output power. So on the left, we have also a 10 kilowatt and a 19.8 kilowatt configuration. And the turbine on the right side is available also in the past, I have to say, as a 10, 19.4, and today 25 kilowatt. And the major driver for these various configurations have been the national requirements, but mainly related to feed-in schemes. I would say to currently deployment, the O design is for the vast majority installed in Denmark and the Asian market, but is actually also being highly deployed in the Netherlands. The turbine on the right side is mainly used for new introduction, new markets, and lately been installed in Germany, Belgium, France, Norway, and later on we'll see a project in Switzerland as well. As said, the layout, the components is equal to each other. Finally, I could say the turbine on the right side, we had a lot of emphasis in simplicity and in lowering the OPEX cost. So we put quite a lot of effort in the simplicity of the layout of the turbine and the actual nacelle. So the T design is somewhat simpler in the layout versus the O design. The turbine itself is what we consider a Danish design. It's also Danish almost from its country of origin. meaning that all the components we source are European originated components. That I can say to the first, second, and third tier of sub-suppliers. What happens besides and beyond that, I don't know. But we do really focus on having a Danish European originated turbine. So, for instance, the generator is German, so are the brakes. The gearbox is Swedish. Our control system and Yori gearing is Danish. The steel is European and has up to now been manufactured and machined by sister companies, and now we use a partner in the Poland and Czech area. All the fiber parts for the turbines, such as the blades and our hoods, cover parts, are produced in our own facilities. The building principle does not derive from larger wind turbine building principle. However, we are using only polyester-based resin and standard glass fiber components. When looking to our export market and internal projects, we are capable of providing training and services for not only our own people or employees, but also for the export markets. Our export is carried out with local partners, which we appoint and develop by ourselves. We do train them in terms of the commercial aspects, in terms of selling, but also for sure in the operational aspects, being how to build the foundation, and how to install and how to service the turbine. And for that reason, shown on the right side of the slide, we do now and then have visitors from our local partners for which we are carrying out training sessions and learning sessions. The pictures on the left side were intended to give you an impression that the turbine is built within 5 to 8 hours, meaning that after the foundation is laid, which is a circular foundation of 4.4, actually 4.2 to 4.4, and in some countries we have even 4.6. We have mainly circular design, but we also have squared design. But having laid down the foundation, we arrive at the site with one turbine fitted on a standard trailer or in a standard container, 40 foot. We install the turbine with two individuals between 5 and up to 8 hours. And then it's basically being commissioned and it is in operation the same day. We are 9 people in service and technology with more than, as I say, 100 years of experience. 6 of these 9 people are working with mainly servicing more than 500 turbines in Denmark, but also coping with supervision in export markets and also installation work and special projects. All our turbines are supervised by a SCADA solution, supervised control and data acquisition, and we call that our solid SCADA. We do have various license levels, starting from end user, giving the user right to view the live performance of the turbine. We are able, from our headquarters in Skjern, to monitor all our deployed turbines. As a backhaul for the SCADA solution, we are mainly utilizing the mobile infrastructure deployed and available worldwide, known as GSM, UMTS, 4G, LTE, IoT, and even 5G. So we are utilizing all the multiple band available. There is a tendency that the 2G and 4G, so the GSM and the UMTS network, is being decommissioned, and the frequency are being moved to the higher bands like 5G and 4G LTE. But our connectivity is able to cope with that. We have a number of turbines also being able to be connected through the Ethernet. So there is an Ethernet port available in the turbine as well. As said, we do monitor all the turbines for the customers who have a service level agreement, mainly our reseller and distributors. We do provide 24/7, 365 days supervision and monitoring. For the, let's say, users not wanting or not having the benefits, we are monitoring them within the daily work hour. We are capable of using the data for optimizing the turbine's performance, but also to optimizing relative to quality. So what I'm saying is that we are using the data available from the turbine to run a predicted maintenance program. We have not yet implemented any artificial intelligence on the data scripts, but one could envision that you could move from preventive to prescriptive maintenance based on these data. The turbine originates every month between 15 and 20 megabit of data. So over the lifetime, it does accumulate to a certain amount of data. All in all, the solid SCADA enable real-time insight and quick response time when needed. Some of the last slides, these are, despite the fact that these are a couple of years old, these pictures, they do show the deployment of our portfolio. We are exceeding 1,000 turbine installed and in operation worldwide. So we do feel that our product is not only well designed, certified, but also now a proven industrialized design. The turbine is also certified according to the IEC power measurement, but we do typically also show real-time data from our installed base. These are some of the examples I have been used in various presentation situations, but what we are trying to say is that they are not only certified, but they are also capable in real life on proper sites to perform as they have been certified. And that is what these slides or these pictures shows. This is one turbine on the left side, actually a Danish located site with a 40-meter rotor producing almost 93,000 kilowatt hours after 12 months of operation. The latter one, or the one on the right side, is a Dutch turbine on a 60-meter rotor, having produced 30,622 kilowatt hours. It might not be the best example. It's only a half year of operation, but it did indicate for the customer and answered the customer's request to understand real-time and real-life experience on the performance. One of the last slides, I know that we have talked about our activities within special projects. We do not only to, let's say, meet the requirements for our employees and technology to have something fun to work with, but we also tend to take upon a number of special projects in trying to push the envelope of the turbine's ability, kind of working outside the standard area of intention and the standard area of for which it's originated, designed for. We have had projects on the northern side of Hokkaido in Japan, and we have had and still have a project on a Greenland northwestern coast. And now we have entered into a project in Switzerland in the canton of Graubünden. And the main question here is trying to understand the feasibility of establishing renewable energy sources or energy generation on a high altitude alpine environment. So we have been provided with a test site starting at just about 2,500 meter height, going up to 2,700 meter. And there we have installed a small wind turbine at 25 kilowatt on a tilt foot. And so far so good. It was actually installed this month, early this month. The challenge was mainly the access to the site, for which we used a material lift, and we also used helicopters for the purpose of lifting up heavy equipment. The helicopter itself was also used to install the turbine, so it was acting as a crane. So far it showed out that we can use almost standard procedures for preparation and pre-installation activities. Now we have to see within the next 12 months how the turbine and the wind turbine application itself performs at these conditions. But very exciting. The project was carried out with a local partner. That sums up my presentation. I think I were allowed to have 25 minutes. I'm open to any questions.
Yeah, thank you very much, Søren. It's actually quite nice to see the turbine on the mountain. See how well it is integrated in the landscape. Is there any question from the audience? No.
Then I would say thank you. And since it's Friday, I will also wish you all...
Ulrich is asking what is the levelized cost of electricity?
I don't know how much time we have, but I do actually have some calculation I would like to show. But in a very short matter, assuming we have 5 meters per second wind available, and assuming that the capex is around 170,000 euros for a turnkey solution, then the turbine will have an LCOE of just about 8.5 euro cent per kilowatt hours. If we add on a 20-year service contract, coping with the spare parts, so the consumables and the SCADA, machine insurance, man-hour, driving cost, then we are on a LCOE of 14 euro cent. If I add on a worst case scenario in which I add on a little bit more OPEX in the latter end of the design lifetime. So, for instance, if I add on additional spares in the lifetime of or lifespan of 15 to 18 years, then we are at a 18 euro cent LCOE.
Okay, thank you.
I hope that answers the questions.
So I would say if there are other questions, then you can just write them in the chat, or maybe you can also put your email address in the chat so that people can reach you with more detailed explanations. But
yeah, it's shown here on the last page.
And we move to the next speaker, who is Alessandro Bianchini, who is assistant professor at the Department of Industrial Engineering at the University of Florence in Italy. And he has a background as an energy engineer, both as a master and a PhD. And he works also as an associated editor for the Wind Energy Science Journal and is part of the European Academy of Wind Energy. Good morning, Alessandro. Thanks for joining.
Can you hear me?
Yes.
Okay, so welcome. Good morning, everybody. Thank you a lot for inviting me. So indeed, it was my plan to attend the conference this year, but unfortunately, this week in Italy is crazy because we have started all the lectures and we have a brand new Master Science degree course on sustainable energy. So you can imagine that it is very complicated, but it is a pleasure at least to share with you this presentation from a distance. So can you see my screen? I think so, because I saw it in Zoom.
Yes, we
so
can.
Should be fine. So the title of my presentation seems a little bit pretentious today, but indeed this is the title of a paper that together with some colleagues we published last year in Wind Energy Science. And let's say the scope of today's presentation is to showcase the kind of work we did. And please let me state from the very beginning that this paper does not want to represent a solution rather than a starting point for stimulating further discussion about small wind turbines. So as you may know, the International Energy Agency, together with the European Academy of Wind Energy, promoted a couple of years ago a program, let's say collaborative program to define or to update the grand challenges for wind energy. And so after a little bit of discussion, small wind turbines have deserved one of the 10 papers on, let's say, representing the grand challenges. And the one I am presenting today is exactly a part of this collection. As said, you can find it open access to at this DOE in Wind Energy Science. So let's say the paper which actually presents the collection of the grand challenges paper is the one cited here in the slide that present this famous graph that Paul Viers presented at Torque 2022. It is called the Viers pyramid, and the sense of this graph is showing what we are doing. So in wind energy, the final goal is to have access to a carbon-free energy. For the moment, we have, let's say, already built these colored blocks. So utility scale wind turbines are already quite well optimized in terms of aerodynamics, of structures. We are able to make wind energy cost effective, and we are already working at plant level. However, the sense is that if you want to make this pyramid really stable and so really push wind energy forward and making the backbone of a more sustainable energy systems, we also need to build these other bricks. So where small wind turbines can find room in this pyramid, I would say here. So we still have to improve small wind turbines as let's say as energy generation system. In the paper, it is written that small machines have not received, which is, you know, that is true. Up to a few years ago, they have not received the same design refinement level than utility scale turbines, but if we invest in them, they could really contribute to the energy mix. And to do that, so to add this brick to the pyramid, our vision is that we need to work on the different levels. So we need to improve the turbines, the structural and construction parts that we will discuss this in a minute. But we also need to work on social sizes. We need to work on at the installation level. It was very interesting to see in the previous presentation an installation of small wind turbines in the mountains. So again, we need to work at different levels, and this is the sense of the paper I will be presenting. So a short, non-linear story of the paper. As you may know, the European Academy of Wind Energy has created a few years ago some technical committees to as collaborative groups to foster the research onto different topics. I had the pleasure to lead the Small Wind Turbine Committee for the first 2 years since the foundation. And one of the very first scopes of the Small Wind Turbine Committee was to deliver a white paper on as you can imagine, on small wind turbines. But what became apparent very soon is that the original plan was to have it on Europe, but that paper was a little bit reductive. So the topic needed a more comprehensive approach, and also we needed to gather competencies and experiences worldwide, because, let's say, Europe is not the only and probably not the biggest market for small wind turbines. So the group became much bigger. We had contributions from other colleagues in Europe as well as all over the world, and also coming from different backgrounds, which is also very important. So the paper had two main scopes. The first one was providing an overview on the status of small wind turbine technology. So if you take a look to the paper, you will see that sections 2 and 3 provide an overlook about the market diffusion, some updated economic data, very interesting, but and also a description of the main technical features of small wind turbines in comparison to utility scale ones. Due to time, of course, I would not presenting anything about this in today's presentation, but if you're curious, you can go and find them on the paper. The second part was, again, defining, for at least from our perspective, 5 grand challenges that we suggest as key to foster the development of small wind turbines in the near future. And please let me repeat that again. We are not saying this is the only solution. Many of you have experience into this field and probably may have visions which are a little bit different from that. But again, the scope of the paper was to restart and stimulate the discussion on the topic, and to try to be as systematic as possible. What we tried to do was first to define a series of unknowns and gaps for small wind turbines, and then try to rationalize all the inputs and all the experience of the authors into defining improvement areas and prospects to address these existing gaps. So, as said, first we tried to highlight at least some of the unknowns and knowledge gaps for small wind turbines, and we turned it out into 6 main categories. The first one is that in general, as you perfectly know, small wind turbines are entitled of having higher levelized cost of electricity with respect to utility scale wind, mainly due to the lack of economy of scales and to higher balance of station costs. The second element, so the second, I would say, drawback is an uncertainty in the actual power curves. So not too many turbines have certified power curves. I was very happy to see before that some good producers are now providing very high quality products, but if you make an average worldwide, this is not always the case. And also we have uncertainty into the local wind conditions, and we will see why. And this in turn come into a poor estimation of the annual energy production. Another drawback is that over the last decades, we saw intermittent incentives, regulations, feed-in tariffs, or whatever between the countries, and they were not only different from a country to another, but also intermittent in time, which makes it very difficult for producers to stay in the market. The fourth element was the lack of openly available data, which are very useful to improve the models. We have to fine-tune the design tools and the estimations of the real production. The final two elements is, the first one is social acceptance and environmental issues. So small wind turbines likely, as you perfectly know, are installed quite close to the built environment, or let's say the populated environment, which let's say exacerbates a little bit the problem of visual impact, noise, and the perception of the populations. And finally, it is apparent that there are still concerns with the small wind turbines reliability and also with problems of certification. So overall, as said, these are not all the gaps for sure, but we tried at least to summarize them into that. So moving from this background, the paper suggests 5 grand challenges that you see listed here, but I would not read them all, and we will try to analyze them a little bit more in detail. So grand challenge number 1 is to improve the energy conversion of modern small wind turbines through better design, control, especially in the case of turbulent wind. So I came from the aerodynamic design. I'm an expert of airfoil aerodynamics in turbulent cases. So this is probably my number 1 grand challenge. So the background is that, as we have said, small wind turbines traditionally did not receive the same level of design refinement, as very often to keep the cost low. And also, they are typically installed in areas that have lower winds and more turbulent and gusty oncoming wind. And so maximizing the energy harvesting in these cases is not easy. And that's why many wind turbines have been shown to underperform in comparison to expectations. So what we can do to tackle this grand challenge, for sure, we need to get a better insight into the impact of turbulence and gustiness on turbine performance. We need better design and analysis tools that are able to account for this so complex blade flow interaction. We need to find solutions to exploit these winds better, which means taller towers or different designs of the rotors, like for example going to low specific power rotors to be able to harvest energy also at lower wind speeds, and multi-objective design, for example, to make very efficient turbines while keeping the cost low. So moving to grand challenge number 2 is improve the prediction and reliability of long-term turbine performance despite limited research measurements. As you know, defining the long-term performance of a turbine is mainly made by combining, let's say, 2 elements. First one is having a good estimation of the actual power curve. Second one is to correctly estimate the resource. And doing this is not always easy because we often lack reliable measured data. And so what we can do to tackle this grand challenge, having data, possibly open access, is very important, especially because we miss mesoscale modeled data for this low wind speed, where the effect of obstacle is very relevant. And that's why we would also need methods that can better model the impact of obstacles into real installations. And finally, we would need to develop methods that prove that small wind turbine technology can really operate reliably over its design life. Grand challenge number 3 is probably the most difficult one and the most relevant one, is to improve the economic viability of small wind energy. This has been discussed also before, so we need to have competitive LCOE. And this is particularly tricky because of the cost of the materials, the installations cost, and also because it is so small wind turbines have not coalesced into a single archetype, which makes the creation of standardized solutions and the creation of economy of scales not always easy. So the actions that are suggested, so we need to reduce the costs, and these can be done by multiple actions. So we can optimize the design, of course, exploring new material, new manufacturing techniques. Very important, try to access standardized solutions that potentially can be applied to multiple turbine models, such, for example, as power inverters. So to incentivize the production of economy of scales, and also reduce some items which are very important, like foundations, tower, and our other balance of station costs. Grand challenge number 4, facilitate the contribution of small wind turbines to energy demand and electrical system integration. So currently we have around 1.8 gigawatts of small wind power all around the world, coming from 1 million turbines. So a lot of very small insertion of power into the grids, and the highly discontinuous power production from small wind turbines can be hampered in some grids, which have restrictive limitations in terms of ramp rate. And so if we want to convince people and communities and politics that small wind turbines are really competitive with PV panels, we need not only to make them more efficient, but let's say to integrate them very well with the grid. So for sure, so the action that we need to put in place, small wind turbine technology must advance to meet the evolving grid code requirements. And if we invest money into that, we also need to ensure that the value they may add, that small wind turbines may add to grid reliability and resilience is properly monetized and highlighted. And also, as you perfectly know, there is an increasing importance of energy storage, so an effective coupling between turbines and storage for a variety of reasons, so load shifting, but also power quality, like power smooth. Moving to the fifth and last grand challenge, it was called foster engagement, social acceptance, and the deployment for global distributed wind market. So NIMBYism is still hampering a lot of potential installations, and so to overcome this issue, we need to enhance the social understanding of small wind turbines, provide real evidence that the modern turbines, as the example we have seen before, are really able to perform much better than their predecessors. We need to put a special attention to environmental impacts, so to ensure communities that the installation of small wind turbines nearby their houses or buildings or facilities is not a risk. And also we need to push and harmonize politics and regulatory aspects and promoting the harmonization of them among countries, because this would really allow the deployment of the technology in a more effective. To do that, the paper suggests 10 key enablers. So I'm running out of time, so I'll go quickly through them. But if you're curious, of course, in the paper, you will find many more details. So the 10 key enablers, first one is the more effective use of air elasticity into small wind turbines. So air elasticity is the base for the design of larger scale turbines. It has been used not that much in small wind, but if you want to improve the design of the new machines, for example, going towards lower specific power rotors or having lighter, more flexible blades, we need to introduce air elasticity. And to do that, we need to also train the personnel of the producers to use the codes and to, let's say, really understand air elasticity. We need to improve in control strategies. So we are seeing a fast transition away from furling towards more advanced control stall strategies. There are also some examples that are showing that individual pitch control, even though it is difficult to be included into small wind due to mainly space in the nacelle and cost, but could provide a real improvement into the production and also an alleviation of the loads, which is again could be potentially very useful to make blades that are lighter and also cheaper. We need to improve the aerodynamic design, especially with focus on low Reynolds airfoil aerodynamics in turbulent environments. This is relevant not only for performance, but also to ensure, for example, a better control when you design a stall control-based machines, and also to reduce noise and to account, for example, for air density variation. The example we saw before of a small wind turbine installed in a mountain is very, very nice, but if you install a turbine at over 1,000 meters, the density change quite a lot, and so we need to be able to account for that properly. Fourth enabler, to have, we have discussed this already, open data, both from wind tunnel and field experiments to calibrate and tune our model. Fifth one, more accurate performance and risk assessment. Again, we have already discussed it. This can be done both with experimental measurements and with the use of higher fidelity methods like CFD. Sixth, variable validation and verification. This is very important, and it is discussed a lot in the paper, because what we could do probably in the future, and you know better than me that design is evolving into this direction. Smaller turbines and more established archetypes could benefit from less onerous requirements in terms of load assessments, validation, and certifications. And this could speed up the process and also promote standardization. And standardization is exactly what we probably need, because it's very important to promote the economy of scale, and this in turn reduce the cost and make the LCOE more competitive. And standardization, as we were discussing into point 6, is also needed for regulations and standards. Coming to an end, so the 8th enabler, we need detailed studies on cost and life cycle analysis, because they are very useful to identify method to reduce the installation cost. We need to make small wind turbines more compliant, as we discussed before, with the grids and more tightly coupled with storage systems. So small wind turbines should probably become variable speed, make full use of AC, DC, AC converters, and they need to be coupled with fast response storage systems to allow for power quality and grid stabilization capacity. Finally, we would probably need to push and promote shaded programs of incentives, new paradigms to support the diffusion of small wind turbines, and particularly we would really try to convince to keep this program alive and stable for a sufficient number of years so that producers can really stay in the market. So this closed my presentation. So the final question is, are we ready? Again, please let me thank all the co-authors of the paper. It was a great working group, and I would say also a group of friends. So many credits to all of them. I am presenting on behalf of all the authors, and let's say I really hope that this paper can further stimulate the discussion and promote events like the one we are attending today, which are very, very important. Thank you.
Thank you very much, Alessandro. Very interesting and very nice to see also many well-known names in the study. Is there any question from the audience? No.
Probably there would be too many, so I think it's difficult to make a question. As said, the paper is quite big. It's 35 pages. And it is conceived to stimulate the discussion, but I really hope we will have some neat and nice advancements in the future, and I'm seeing part of that already in place. So I'm following some of the companies. I saw many of them participating here, and the progress into new products is very interesting.
Yeah. And also, you can put the link in the chat. We can include it also afterwards in the proceedings. But for now, you can also put the link of the work in the chat so people can access it and read it with some calm as well. But yeah, otherwise, thanks a lot. And I hope that you have the chance to join us in presence next year. It would be really nice to have a big in-presence event so that we could have a lot of networking as well. But yeah, so far that's what we have. So thanks for joining also with very short notice.
I'll try my best to attend next year, I promise. Thank you for inviting me, and I really, it's a pity that I cannot join you for the entire week, but I need to run lecturing in a few minutes, so sorry for that.
No worries. And it is on YouTube afterwards, so you will not miss anything.
Perfect. Thank you. Bye-bye.
Bye-bye. Thanks a lot. So we move now to the other side of the world. We go to Australia with James Brandley, who is CTO of Diffuse Energy and has a background of mechanical engineering and a PhD at the University of Newcastle, where he focused on materials storing thermal energy. And then after that, he co-founded Diffuse Energy, of which he will now tell us a little bit more. James, are you there?
Yep, I'm here. Do you hear me okay?
Yes. Good evening.
Yeah, so it's a late afternoon here. So once again, thanks heaps for inviting me. It's great to be part of all of this. Sorry, I'm just trying to... So hopefully you can see my screen now properly. So yeah, we're, I guess, one on the other side of the world, and also probably a bit of a change of pace from small wind turbines to really small wind turbines. So
James, really if you switch to presentation mode, we see also the next slide.
What's going on there?
There should be something like switch display settings, maybe?
Broken everything now. Why has it done that to me?
You go on display settings on the left, should be... Yeah.
How's that?
Perfect. Thank you.
Okay. Yes. So today, I'll give you a bit of introduction to our small wind turbine. Over the past couple of years, we've been running a project with the Australian Renewable Energy Agency, funded by them, which is kind of centered around the application of our turbines in remote telecommunications and sort of stretching into remote data applications, predominantly on farm. Then I'll talk a little bit about some complications of control of micro turbines, and further to Alessandro's great point just previously, some difficulty in predicting site power output, and then later about some supply chain difficulties which we may not be alone in. So as you said, myself and co-founder Joss Kesby came out of the University of Newcastle. Our core ability is the ability to design a diffuser augmented wind turbine quite well, I guess, and that was out of Joss's PhD. So there's a photo of our little turbine there. In the application of remote telecommunications, predominantly we're competing with the cost of diesel. So many sites in Australia at least run wholly on diesel or on diesel with a supplementation of solar, but typically there's a diesel generator running there once a day or more frequently. So the idea was to offset some or all of that diesel. The other great thing about telecommunications is we can mount directly onto existing infrastructure. And, you know, as we all know, wind is quite complementary with solar. I don't think I'm telling anybody anything new there. And we had remote monitoring so we can see what the turbines are doing in real time. So a little bit more about our turbine. So most of the turbine is made here in Australia, with the only thing really is the generators. There's no one in Australia building generators, unfortunately. So it's only quite small, just under a metre in diameter, less than 20 kilos. Quite happy to survive in more than 150 kilometres an hour. We've measured that a couple of times out in the field. Rated output of 200 watts, peak of around 650, depending on some system parameters. And everything on the turbine is designed to last for 20 years. So the plastic has a 20-year UV protection, and obviously stainless steel for most of the components. There's some aluminium components, but they're a marine grade cast aluminium. So yeah, the project that we've undertaken over the past couple of years has been with ARENA. So ARENA's fantastic in kind of looking at new technologies in the Australian landscape. The project originally was meant to go a little bit shorter, but unfortunately COVID happened just after we started, and that kind of, you know, made life difficult for all of us, as we all know. Partner companies, so there's 3 partner companies that we installed sites with, predominantly on the East Coast, but a couple on the West Coast of Australia as well. Here's some of our installations, some on larger telecommunication systems and some on some quite small ones. For example, the one there down the bottom with the 2 turbines is in southern Australia, on a fairly peaky hill. And you can see for probably 20 kilometres in every direction, quite flat. So it's like a really good spot for small wind turbines. And in the top left-hand corner is on a more traditional telecommunications tower up on the escarpment on the east coast of Australia. We did install these on smaller telecommunication systems, so more point-to-point array rather than sort of the one-to-many 4 or 5G standard telephone towers, which use, you know, upwards of 10 or 15 kilowatts. So a typical installation for the kind of sites that we're using run on DC. And I guess the fun part is that you've got a solar panel and a solar controller, a wind turbine and a wind controller, and a diesel generator and a diesel generator controller, all sitting on a common DC bus, which makes control of the whole system kind of interesting. And then on the output side, they'll have, you know, DC or AC systems running the communications. Predominantly in Australia, it's either 48 with some 24 volt DC and a very few 12 volt DC, but that's quite rare. So a big part of our, I guess, we designed the turbine back in sort of 2016, 17, did a whole pile of wind tunnel testing and thought we're pretty clever because we'd made quite an efficient turbine. And then once we stumbled into the telecommunications market, realized that we needed to be able to get the electrons out and put them in their systems. And that's where the fun kind of started. So our control has evolved over a couple of years. And I guess the biggest challenge for us is twofold. One, normally it's assumed that a micro wind turbine is going to have a person around in a storm. Our turbines are mounted out in the middle of nowhere. And so if it does blow 150 kilometers an hour, there's no one there to, tether the turbine or shut it down. So we needed to be able to stop the turbine in those situations. And so we actually short the windings on the generator, and that stops the turbine in much less than a second. And the other is for small turbines, the reaction time of the turbine is really, really quick. And so typical small wind controllers are kind of based off a solar controller, and the control loop on those just isn't quick enough to keep up with what happens. So our turbine controller can stop the turbine on a range of conditions, being over current or over voltage, or if the thing gets too hot, we can shut it down as well. That's a problem in Australia because it gets up to 45 degrees out in the middle of the outback. So appropriate control of small wind turbines is pretty important. This is from the early days. So this is two power curves. One of them, we basically had a calculation error in it when we were first doing some testing. But you can see these two power curves aren't a mile apart. And one of them is the correct one, being the blue data there. The other one was incorrect, being the green data. These are two turbines that are mounted or co-located on a site. They're about 6 meters apart. And you can see here that there's a 37% power difference between those two turbine outputs just based on the control curve. Realistic, like they're orthogonal largely to the prevailing wind speed, so that they don't interact with each other too much. So it just shows the importance of having good control. So I didn't mention earlier, our control loop, operates at 5 kilohertz. This is just for the nerds out there, a piece of data. So our turbine will accelerate if let go from sort of 600 RPM to 1200 RPM in well less than half a second. Sorry, question? Sorry, that's okay. And then with our remote monitoring on numerous occasions, we've measured well more than 100% changes in power output in quarter-second intervals. And so to keep up with that control and, not have the turbine run away on you in gusty conditions is pretty important. The other thing we had was remote, so that we could look at our turbines and see what they're doing, was this remote monitoring. We also plugged Luft anemometers into these so we could measure wind speed. We can log these up to 20 hertz. Don't do that very often. It's usually only when something exciting is happening. The dashboard will display information at about 2-second intervals, but we can download the data at full speed. And that's allowed us to kind of see, what's going on in edge cases to help us refine our control algorithm. So the outcomes of this last couple of years of testing is we've seen that originally we were aiming this at the larger point-to-point antenna arrays, which sort of sit around 700 watts to 1.5 kilowatt continual load. Unless it's a really, really good site, our turbine's a little bit, single turbine's a bit undersized to have a good impact. Like, it has an impact, but it's not really a good enough impact. However, smaller systems like the on-farm systems there that sort of run down, 250 watts is probably a common load on those. The turbines do really well at complementing solar, and we've got quite a few sites now that the diesel generator or petrol generator is just there just in case, rather than operating all of the time. Something that we found is that very careful consideration of site selection is super important, and I'll show a bit more on that in a moment. But we've put some turbines in places where we've got it wrong, and the output from the turbines just been terrible, to be honest. And so getting that right so that you don't annoy customers is pretty critical. And just for fun, high frequency, like logging 10 hertz data out in the field in the middle of nowhere, racks up an awful amount of data, but is also kind of problematic just to have a system out in the field that's doing that long term. And so it's not recommended for just normal use cases. It's okay for, if you want to get your science on, but not great for a long-term solution. So more about power prediction. So we use a number of, of wind prediction data sets. So one that was produced by the CSIRO, who's Australia's science body. There's a little image there on the left-hand side. You can zoom right into about 1 kilometre square. It'll give you average wind speeds over history. And then the other data set that we use is the NASA wind data set. Oftentimes they'll agree quite well, but occasionally, and here's an example here, you can see, one's predicting 1.2 kilowatt hours a day, the other one's predicting 0.2 kilowatt hours a day. And so when that happens, it's, you kind of start guessing. We've refined, there's a fair bit more that goes into our calculation here. This is just sort of the back end of it. And we've been refining that over the last couple of years, and we've gotten a lot better. But every now and then you do find a site where you have this huge disparity. It's not very confidence building for either us or the customer to go and install a site there. And for micro wind turbines, it's not really feasible to go and do a long-term wind study normally, unless it's a very critical site that's got big problems. And then the final part is supply chain for our controller. So we spent a long time developing our controller, and it uses a lot of components that are fairly unique, so that they don't have comparative parts. And we've had components now that have been off market for just about 18 months. With no clear end in sight of an ability to get them. And furthermore, the parts that we can get, the bill of materials cost has nearly trebled. So we're kind of in a position now where we've got a potentially long wait ahead of us to get our controllers back on the market. So we've been, we ran out of controllers about 6 months ago. So we're kind of in a wait and hold situation at the moment, which is not the greatest place to be. So that was a fairly quick one. I wanted to leave some time for questions, if anyone's got any questions.
Yes, thank you very much.
There's no questions. I'll thank everybody for your time and allowing me to come and present.
Thank you for joining. Is there any question from the audience? Doesn't seem so. So then, as usual, you can just put them in the chat or write directly to James. Thanks a lot for joining. And now we go to the next speaker, who is Luis Cano. And he has a background as an electrical engineer, and he's senior researcher in the wind sector for CIEMAT in Spain. We already heard this name a couple of times in this conference, so you can understand it's a nice working group that we have on here. His focus is on wind turbine test and resource assessment, and he focuses also on hybrids and energy storage systems. Luis, yes, we can see your screen. Welcome.
Can you hear me?
Yes, perfect.
Okay. First of all, thank you very much to Nordic Folkecenter group for inviting me to make this presentation. I was there in your installations several years ago, and I think it's a great place for sharing experiences and knowledge about wind energy. So, well, the presentation is about the test site calibration and assessment of a 100 kilowatt turbine power curve, but using LIDAR measurements instead of met mass anemometers. Okay, well, this is our test facility in Spain, in a center that is called CEDER. That means, this in Spanish is Centro de Desarrollo de Energías Renovables. This means that Renewable Energies Development Center. Here there is some pictures about our facilities. Here is a blade test bench. We have 5 positions. We can measure and test small wind turbines up to more or less 100, 150 kilowatts, more or less. And with different wind resource regiments from class 4, that is, for example, the third test site 5, test 43, that is where the 100 kilowatt wind turbine is installed, or we have just other positions with class 1 wind speed. Well, the test sites is called PIPA 3, that is in our facility. We have carry out 2 different tests, 2 different site calibration tests, one with 2 anemometer mast, and we have repeated the same experiment with 2 remote LIDAR systems. You can see here the picture with both anemometer mass and with both LIDARs. Well, first of all, we have made an assessment of obstacles and the terrain in accordance with the IC standards, the new IC standards, the IC 61412.5, that is called now assessment of obstacles and terrain. The results is that this installation is, for this machine, is a complex terrain with more or less an average terrain classification 2 or 3 in accordance with the results shown in the IC 61412.5. Well, this is the wind turbine. This is a Spanish wind turbine. It's called NET 100. It has a 24-meter diameter, and the tower height is 36 meters, with a specific power that is around 220 watts per square meter. And here there are another general characteristics with cut in, cut out, the clash regulation, and so on. Well, the equipment that we have used is two LIDARs that from the company ZX. In particular, the model ZX300. The measurement period is for more or less 3 months, from March to June in last year. And we have programmed the LIDAR for 11 heights that you can see from 12 meters to 100 meters. And we have, as you can see previously, two positions with a distance of 70 meters, more or less in the west direction. That is our predominant wind direction in our center. Well, the first of all that we have to do with the LIDAR data is use some filters to get data that are relevant because LIDAR has some difficulties to measure, for example, with foggy days or rainy days, and there are some errors or mistakes in the data that we have to filter. Also, we have for the procedure that use this LIDAR to measure, and sometimes it produces an disalignment of all with low wind speed regimens that we have to filter also. And finally, we have obtained our valid sector for measure the power performance of the wind turbine. So you can see that is more or less north, west, and south. Later, we have obtained the equivalent rotor wind speed, taking into account the three measures that you can see is the height about 2/3 of the radium, and height less 2/3 of the radium. We have obtained also the wind shear of each wind speed, and we have prove or test the diurnal cycle of atmospheric stability, and you could see that at night and during night and during day there are differences in the turbulence and the wind speed profile. Well, we have used the method 1 in the IEC standard. This method uses beams of wind direction and wind shear, because in our case the wind shear is significant. And we have measured how many data and which is the percentage of in where wind shear, or the coefficient wind shear is more than 0.25. And it's more or less around 36% of the data, and for this reason we have used this method. And this table are the results of wind speed ratio that we have to use in each wind shear exponent and each wind direction to correct the flow the flow between two LIDARs, the flow and wind speed from the two LIDARs. Well, we have also the quality checks that are exposed in the IC standards. We have assessed the significance of SEER, and you can see that it's the linear regression is, or well, we had do it for each wind direction bin. We have also fulfilled the completion criteria for wind direction. We have enough data to obtain that this test is valid. And finally, we have made a check, the comprehensive check of the measurements. And well, we finally make the change between the adjustment wind directions bin, and we see that we don't need any additional standard uncertainty for this method. We have finally obtained the statistical uncertainty using the K-fold cross-validation. That is the method that is exposed in the standard. And finally, we see that taking into account the LIDAR, it's better to use equivalent rotor wind speed. And well, we see that the A uncertainty, well, it's in Spanish, but this is the A uncertainty for the calibration is site calibration is more or less that 0.006, and the other case with using only one measure is 0.001. And also we have the comparison between the linear regression among LIDARs and among anemometers. Then more or less we can see that the bias using anemometer is higher, less higher of the bias using the LIDARs. Okay, well, this is the data obtained for the power performance tests using the LIDAR and the correction using the site calibration test among the data of the LIDAR and the SCADA wind turbine. And well, we can see that in many cases the differences among in each wind direction among the wind SCADA data and the LIDAR wind speed ratios corrected by site calibration test are important in some cases. I mean that more or less here we have around 1. Here we have some points in 1.2. This is relevant, I think. Finally, we have measured the vertical wind speed profile in order to obtain the rotor wind speed. And well, we could see that the versatility of use the LIDARs is that you could put 1, 2, 3, 4, 6, whatever you want in the rotor height. Because, well, in this case, more or less the half height is the average, but we have, depending on the terrain, you could using an average wind speed that is not exactly realistic. Okay, finally, the result of the power performance curves. We have four power performance with using the rotor wind speed rotor equivalent wind speed, or just only the half height wind speed with the LIDAR and with the SCADA, and without correction and without wind shear correction or with wind shear correction. More or less, we see that the SCADA power performance is significantly less than the performance that can use with the real wind speed that the LIDAR could see in the position. So it's well, this is a question of yaw misalignments. Suppose that the operation of the wind turbine, but it's significant the difference. So as a conclusions, we have measured and shown a site calibration using remote sensor devices like LIDARs. And the use of the standard IC is 61,412.5 with good results. But this site calibration must be validated in more complex terrains with a higher ruggedness index that, well, we are working in do it with other research groups. The other conclusion is that the use of remote sensor devices gives higher flexibility in order to data obtained with the SCADA and perhaps with some algorithms that depend on the terrain could be improve the final power performance of the wind turbine. And well, that's all. Thank you very much for your notation. And well, if you want to do some questions.
Thank you very much, Luis. Is there any question from the audience? It doesn't look like, right? No. But then, yeah, then they can just contact you should there any question arise. Thanks again for presenting.
Thank you, Daniel. Thank you, Daniel.
And we will now have a break up to 10:40 our time. So that's about 15 minutes, I would say. So yeah, take the chance to stretch a little bit the legs so that we can get ready for the remaining part of the conference. See you in a couple of minutes. Is it on? Yeah. So, welcome back. We have now a presentation with a lot of speakers, and the reason for that is because they made a joint study. It's students from a university, Mondragon University in the Basque Country, Spain. And well, of course, fair enough, they are going to present all together. So I would like to welcome Oihan, Aitor, Asier, Ander, and Kristian, who, as said, they are studying at the Mondragon University in Spain. And they have different focuses. In general, they are all in the sector of industrial electronics and renewable energy, electrical machines, and also doing research work in this sector. I could see two of you coming in. Yes. Are you there? Let's see, because Søren coming in now.
Is it pinned?
No, I took away the pin. Yeah. Oihan doesn't have the microphone and okay, now they're coming in the others as well. So Kristian, Asier, Oihan, are you there?
Hello.
Hello. Good morning.
Can you hear to me? Good morning.
Good
morning. One moment.
Yeah. How you are going to present?
I present for all my colleagues.
Okay, perfect. So yeah, thanks for joining. We are glad to hear the results of your studies, and the floor is yours.
Okay, thank you very much.
Kristian, wait, because I don't know if Aitor is here actually.
Okay.
Yeah, we can wait a moment. There is no problem.
We are connecting from different places, so
yeah, no worries.
Problems.
It's good enough that you could join.
Okay. You could see the presentation?
Yes?
Yep,
Yes.
you can see. Yep.
Yeah.
Perfect. Okay, so when we are ready, we're gonna start.
Yeah, whenever you want.
We are all, Oihan, we are the fourth. What is it?
I don't know about Aitor, because I guess he's coming, but not. He wrote before 10:45 he will be ready, so hopefully he will be coming soon.
Okay, perfect.
We can wait a moment for him, it's no problem. Meanwhile, we are waiting for the rest of the audience, just so that you know. So we got in contact with the professors who made this study, and yeah, they wanted to come, but then at the very last they couldn't because of other engagements. So then they asked the students that took part in the study to present, and yeah, of course we are always happy to welcome students and to introduce them to the international wind community. So we are glad that the teachers the professors could give this option to the students, and we are glad that the students could take it despite all the other work and studies that they need to do at the same time.
Thank you very much for your words. Our teachers are really busy today, but
now he's coming.
Hopefully we can be at the level of our teachers someday.
Good morning, Aitor. Can you hear us? Aitor? Aitor, can you hear us?
Hi, yes.
Hi, good morning.
Good morning.
So, whenever you want, we are ready.
Okay, thank you.
Okay, perfect. So we are going to start for the presentation. Hi everyone, we are the 5 students from the Mondragon University, and we are going to present a summary of our recent job. That it's the low-cost maximum power point tracking strategy and protection circuit applied to the Ayanz wind turbine with the screw plates. So first of all, we want to thank you for the invitation to expose our job, and congratulate you from the event. Okay. So this is going to be a summary. All the information on the technical data is available in our article that is published in Energies. If you scan the QR code, you can read the article, or if you have some interest or questions, you can write to us, and we are very happy to respond to you. So the index of the presentation will be the initial context of why we have done this project, the characterization and comparison of the wind turbine compared to other ones, the low-cost maximum power point tracking strategy, and the electronic protection circuit, and to finish the result discussion and some conclusions of the work. So the initial context of the project, we are going to first of all locate our university and us. We are located at the north part of Spain, between Spain and France, at the Mondragon town in the Basque Country. And here Spain is known from the solar and those kind of other renewable technologies, but we also have too much wind. And here in the north part, there are lots of wind parks. The last 2 years, for example, in Spain, around 2.5 gigawatts of residential self-consuming power plants were installed at residential and industrial areas. So a lot of small self-consuming installations have been installed in the recent years, but all those gigawatts are installed in solar technology. And we have one question: why isn't wind energy installed for residential use? First of all, the spares requirements are higher than the solar. The energy efficiency of the small wind turbines is smaller compared to the big ones. The initial cost and maintenance already. The permits and regulations, for example, have some blades, and in residential areas, we don't want blades or near from kids or colleagues. And the wind variability, these kind of wind turbines are situated or in the middle of buildings or towns, and the wind they are not very laminar or good. So we have used the historical knowledge from Jerónimo de Ayanz and Beaumont to resolve or to propose a solution for contemporary issues. Jerónimo de Ayanz in Beaumont, it's an inventor from Navarra, Spain. Navarra is it's near from our university where it's located, and this inventor has invented some really useful things. For example, the steam engine, the air conditioning, and the first concept of the submarine. Also, Ayanz have patented in 1606 helical blades with an enclosure. So, horizontal axis wind turbine with a tube that Ayanz is supposed to become more efficient and more safe to the people. So we took this concept from Ayanz from the 1606, and we have make a study to an actual commercial wind turbine.
Okay, thank you, Kristian. So in this chapter, I will explain how has been carried out the characterization of this wind turbine, and also I will explain how the performance the Aitor turbine, the performance of the Aitor turbine has been improved by incorporating an enclosure, as it had mentioned Kristian. Okay, so the first step is to familiarize with the wind tunnel that has been used during this project. This wind tunnel is commanded in frequency. So we will control the wind speed by changing the frequency set point. To obtain the wind values that the Aitor turbine is receiving, an average has been calculated from the winds recorded in 9 different points. In this way, very accurate results have been obtained. Once that we know the airflow that is generating the wind tunnel, it's time to know more about the Aitor turbine that has been used in this project. As you can see, the chosen wind turbine is a commercial model Lion F1 AMW. It's a permanent Mayen synchronous machine, which is mainly oriented to urban utilization, as it works pretty well with low wind speeds. Finally, you can see on the right bottom of the slide the electric power circuit that has been used. It is composed of a generator, a 3-phase rectifier, a capacitance, and a variable resistance. Okay, so in this slide, we can see the performance of the Aitor turbine at different wind speeds. In the first graphic, we can see the obtained maximum power, which is around 11 watts. To understand the second graphic, first we need to know what the CP coefficient is. By definition, the CP coefficient indicates the efficiency, which a wind turbine converts the kinetic energy of the wind into electrical energy. Now that we know the maximum CP obtained in this first experiment, the CP obtained in this first experiment is around 0.15, and is calculated with the formula that you have here. Okay, so once that we know the maximum power and CP values that we can obtain it from this commercial turbine, we have added a metallic enclosure to the turbine, mainly for two reasons. The first one is to follow the Ayanz patent, and the second one would be to find out if this enclosure improves the performance of the turbine. Moreover, with the addition of this tube, we are able to minimize the visual and acoustic impact of the turbine. Also, we can incorporate an anti-bird mesh to prevent any bird from getting into the turbine. Can you? Yes. Okay. So in this slide, we have the comparison between the performance of the wind turbine without the tube and with the tube. As you can see, the power and CP values obtained in the experiment with the tube are much better than the obtained ones in the experiment without the tube. At a maximum wind speed, the obtained power value is near 63% higher than in the test without the tube. As for the maximum CP value, it can be observed that they improve by 50%. Yes, here are okay. So therefore, it can be said that the tube is capable of capturing more air streams and direct them towards the turbine rotor. And in this way, we can increase the CP coefficient. One thing that we have tested is that if the wind turbine with the tube is not properly aligned with the wind direction, the generated power decreases significantly. For that reason, we have implemented a simple vane. You can click. This is the vane that we have added. And eventually, here is a demonstration video of the auto-orientation capability of the wind turbine. As you can see, the turbine orientates correctly and starts generating electricity. Okay, you can skip.
Okay, so now I'm going to speak about the low-cost maximum power point tracking, or MPPT strategy we have implemented. So in case someone doesn't know what I'm talking about, the maximum power point tracking is a strategy that maximizes the power generation, so that in each wind velocity we can extract or reach the maximum power. So our group proposed a simplified power electronic conversion stage for small wind turbines, substituting the DC-DC converter and microprocessor that are typically used via three-phase impedance at the AC side. And we have some advantages, such as we reach quite a good MPPT approximation, as you will see in the next slides. It reduces the cost of the product. We use less elements so that we achieve we are close to the MPPT curve, and reduce the complexity of the system, for example. Please, can you pass the next slide? Yeah. So the idea is to take advantage of the variable voltage drop in the AC side of the impedances, as you can see in the below circuit. This voltage drop is in function of the current that crosses the impedance. If the wind increase, the power generation increase. Increase the AC current amplitude, since the DC voltage is maintained constant in the right part, as you can see there. So first of all, we decide to test and make many tests so that we find the DC voltage optimus that was 40 volt. So we installed 3 batteries of 20 volt each in series. There you can see in the right graph in red the MPPT curve that is ideal, and we want to achieve it. In yellow, only with a battery, and in blue, what is our main goal. And finally, you will see that we are near to it. So secondly, once we have determined the DC voltage, we implement the impedances. So to make it faster and to analyze more values, we use the MATLAB Simulink R2022A electrical engineering library software, and we we implement capacitance and inductive series impedance. So to see what was happening or what could happen. In the left side, you can see the capacitance impedance graphic from 1 nanofarad to 200 microfarad, and you can see that they are not good results. They are not results. So we pass to the inductive series impedance, and in the right graph. And there you can see that there is a range of inductance that increase in all the wind speed. So for example, on analyzing the graphic, we take 0.32 Henry as a good result. And then in the next slide here, you can see the last circuit implemented with the 0.22 Henry inductive impedance and 40 volt in the DC side. And left side and right side, left side is simulated graphic and right side experimental graphic. You can see that the result that we are, the simulation result can be confirmed in the experimental test. So we achieve, or we get closer to the blue line in both cases, that is the MPPT ideal curve. And the red is the line with the impedance and the battery. So we get more power and we get close to the maximum power in each wind velocity.
Please. In this part of the presentation, I'm going to talk about the protection circuits. Specifically, I'm going to talk about the protection circuits attached to the batteries which are charged by the aerogenerator. This protection circuit has two main functions: one to protect from overcurrent the batteries, and the other one to supervise the voltage limits the battery has. It's important to mention that 3 different boards have been made, one for each battery that can be connected to the generator. These have been of 12 volts, 24 volts, and 36 volts respectively. Taking into account how the circuit works, we have a diagram here on the left side of the slide. First of all, batteries must be connected to the electronic circuit, and then the voltage they have is supervised. If the voltage is in the range AB, what does this range mean? Is the range where the optimum charge of the battery happens. It is called this way because as we have 3 different boards, if numerical values were put here, it wouldn't be so understandable. So if we are inside this positive or very efficient charge range, the generator is not braked and normal operation happens, which means that batteries are charged. If we go out of this range, the generator must be braked, so it's short-circuited by a relay and protection activates. Batteries are disconnected from the circuit. It's very important to short-circuit this generator. When we disconnect the batteries, the load disappears from the scheme. So the generator starts to spin faster and faster and faster with strong winds and can cause mechanical issues. To obtain the previously mentioned functionality, here we have in the top part of the slide the electronic circuit design. It can be seen as an addition of different sub-electronic circuits, such as in blue, the comparator window, in red, the Schmidt triggers, in yellow, the relay governance, in fourth, the relay in green, and finally, the fifth, in purple, the bus capacitance. If you have any doubts of the circuit, you can ask me when the presentation finishes, because we are not going to explain now how all the circuit works. Worth noting the importance of the efficiency of the board. It's not logic to create a board which consumes half of the power we generate. If we generate 30 watts and we consume 15 watts in the protection circuit, is not logic. So efficiency has been a very important point for us. So the power difference between the output and the input of the board is minimal. Important to mention too that the values that appear in the lower part of the table, in the lower part of the slide, are theoretical values, are not measured values in the board itself, and they do not take into account the rectifier losses. Another important point is the cost. Nowadays, when we are producing or we are going to be using this kind of boards in the industry or in some applications, the price is very important. And the industry standard for this kind of protections are microprocessors. So if we take into account the standard microprocessors and these boards, it doesn't depend, the 12, the 24, or the 36 volt board, they are much cheaper than all these microprocessors. And in comparison, they do the same work, being much more cheaper than them.
Okay, so now let's discuss the results and give some context about them. Please get to the next slide. Okay, so here we can see quite a standard way of comparing the wind turbines between them, which is usually using the CP and lambda coefficients. CP is basically, as Aitor mentioned before, the coefficient of the wind turbine achieving or capturing the wind turbine, the wind kinetic energy, and the lambda is basically how fast are the blades comparing to the wind speed. So as we can see here in the context, our wind turbine is quite well placed because the blade's speed is quite slow, which is, we will see later, quite beneficial, but the CP coefficient is quite high, nearly as high as the Darius or its variants, or even a three-blade horizontal axis wind turbine. So please go to the next slide. Here we can see a bit more of a comparison between the different points, and especially the benefits from this wind turbine are the low rotating speed of the blades, which reduces the noise, reduces mechanical losses and stresses, which will also reduce temperatures in some parts of the generator. And also, as we mentioned before, it's quite an interesting achievement to introduce the prevention for the birth deaths. This will make a quite, how to say this, a quite interesting point in which a bird will not go into the wind turbine, will not die. So it's pretty interesting for urban cities or urban places. You can go to the final slide. Okay, so let's conclude this. This wind turbine was patented for more than 40 centuries ago, in 1606, as Kristian mentioned before, and it still has pretty good feature for the use in urban and residential environments, as said before, because no bird will die, and even the screw blades cannot be seen, which is also pretty important for some people. And then the low-cost power conversion and protection electronics aim to facilitate the integration of small-scale wind power. This is quite important because usually the cost of the electronics is quite high, which makes harder for the small wind energy to be placed or to be useful. And well, all this analysis has been shown in open access, as we have said before. It's free for everyone. You can read more details about this study about the Ayanz wind turbine in our paper. You can scan the QR code if you want. And we are open now for your questions, if you have any.
Thank you very much. And I just noticed that I did a mistake while reading the program, so our break should have been a little longer. That's why you were probably surprised you were on a little earlier than expected. So I apologize for that. Is there?
Yeah, that's why Aitor was a bit late. So, but no problem.
Someone in the audience about the work. So you put the contact. If someone gets some question, can they contact you? Can you put an email or something, or should they refer to your professors?
They can contact us if they want. They can also contact our professors. We are open to answer any question, all of us.
So if you can put the mail in the chat, then maybe someone then will drop you a mail with more information. Yeah, but otherwise, thank you very much for the presentation. So now it's my turn to me on board. So I will need your help, Joachim, on set up the. In which they were mentioning testing, in which they were also mentioning us as testing facility. And actually the reason of this series of conferences is lying back on the fact that some years ago in 2019 we established a new test facility for small wind turbines, which was supposed to expand the capacity of the current one that we have since the beginning of our activities. And as part of the project activities, that was also organizing conferences on the topic. And then we saw that there was quite some interest on these conferences, so we continued also when the project officially finished. But even if the project finished, the test center remains. And we remain positively welcoming to all kinds of ideas that you would like to test. So here you can see a picture of maybe Joachim, if you can set the picture here, not to gallery, just to only one. Yes, perfect. So it's easier to see. So this is a picture of our newest test facility with 3 turbines that were on test, and 2 of them were actually have actually been presented here. The companies have been presented here. So we have the first one from the left, it's a Turbine, and the last one, it's a Viking Wind. So both of them have been now on the conference. So our goal, both as Folkecenter and as a test center for small wind turbines, is to try to come as a help for those small companies that are starting up or that are not so huge that they don't have their own test facilities like the big wind has, for example. So that has been basically the way of working of Folkecenter since the beginning, now we are 40 years old, so has been quite a lot in this direction. But even if this could see a little bit of old-fashioned, let's say, what's the reality is that we keep on seeing more and more people coming in with ideas, and then some of them, they are going ahead, some other are not. But this flow of ideas, it's really promising. And we really see an importance in having testing facilities that can prove the concepts. So why is it so important? Because first of all, we are independent. So when you look at all the nice things that you will see online on some wind turbines, some very cheap ones maybe that you find even on Amazon, you will find power curves, you will find all kinds of information which often have no really a scientific value. They are made with Photoshop. So being an independent institution, our task is to guide you through the process if you want to, but also to say, well, this doesn't work. And then if you want to continue in that direction, that's of course up to you. But we are not going to say, just because you have tested here, we are not going to say the turbine is good. We are going to say what it is the reality. And why is it so? Because, well, I will come to that now. Just so that for those of you who don't know Folkecenter, we are located in the northwest part of Denmark, And you can see in the picture, it's a quite big area. It's 10 hectares of playing with renewable energies, with all the new developments, and we have been doing that in the last 40 years. We are also a point of contact between universities and the small companies, small and medium-sized companies, because often these small companies are a little afraid to go to universities because they see there is a gap sometimes in the educational level, let's say. So when we get people with a very nice idea on a wind turbine, this person might not be an engineer or a PhD, might just be a blacksmith. Not because of that the idea is bad, but of course that poses some initial barriers when you want to get to a higher level, to get to test. So when we are in the middle, we can try to balance this and try to make the two actors talk together in an efficient way. And then back to what I was saying before, why is it important to have independent testing? Because as our founder was saying, if you have a bad product, it's not only harming the individual company, it's harming the whole wind industry. So those who say wind turbines don't work, small wind turbines don't work, that's not true. We have seen that it will work. We have plenty of success stories, plenty of companies that are doing the right thing. But it's also true that we have a lot of companies that are not doing the right thing, that are just marketing a cheap product and doing it in a way to catch the customer, but don't really care what happens after. And then someone who gets tricked in this way, then afterwards will not get another wind turbine again. So it's a whole damage for the industry. And yeah, so our task is to be independent, to test your concept, and to try to turn your idea into a reality. And that depends basically on, we have a set of steps. The first one is, of course, we need to know that you have an idea, so you need to reach us and we can start a discussion. We can see how far are you off, or are you already almost on the idea. And the good thing is that we have a very experienced team, so we can count on this experience to avoid you doing mistakes that have been done already previously by other companies. So then, let's say the product it's not sufficiently good, then there needs something to be improved. Good. Then we start discussing it and we start testing, and we keep on this process back and forwards up to the moment we have something that we are satisfied of. And by we, it means us as institution and the person or the company who is hiring the service. And then once everyone is happy, then we go further and we can go to help you towards the certification process. And then finally, the selling part, that's of course your task, but of course there can be also tasks involved in that sense for us. We have developed this package part. That's mostly a marketing part, but it's just saying we are flexible. We don't need to come and be involved in the whole process. You can just come in and rent a test spot and then run your own tests. That's perfectly fine for us. If you want some help for us, then you buy ours, basically. And if you want more specific tasks, then we take a discussion, we see if we can do it. And this can be anything within this process. We have done also a website for one of the wind companies. So there is a set of services that we can provide in this to support you in this part here. And in terms of infrastructure, we have two testing facilities. We have data logging with quick internet. So yeah, you don't need to, how much is it? Every 30 seconds, every minute, we collect the data.
We collect data every second.
Every second. So, and then, yeah, then elaborate them. So, and then we have facilities also for staying here. So if you need to come from abroad, then you don't need to get mad in trying to find a hotel around. And we have also a very equipped, fully equipped workshop, which you can use to do the modifications you need on the concept. And as you can see from the picture here, wind here is not something that to joke with. Here we get really high wind speeds, and it's actually one of the places in Denmark with most wind energy as well. So you have the advantage that you have a lot and at high power. That also means that your machine needs to withstand that. And that's of course not always the case. But of course it might be seen as a little bit violent picture, but that's what happens in real life when we get a storm. And of course, if your turbine cannot cope with that, then it's something to take in consideration, because if it fails in our test field, it's not too bad. But if it fails when you're already selling it and it's out in the market, then it's really expensive for you. So we have good average wind speed, as you can see, and we have also the option of testing in 2 facilities, as I told you. They are 40 kilometers away from each other, so it's not so comfortable in that sense, but it is comfortable in the sense that you can test different things. So if you are at an early stage of development, then what we suggest is that you take the one that is near us, because you are nearby the workshop basically, so it's easier to have quick fixes. It's also easier to the accommodation and so on. And then when your concept is ready, then if you want, you can move it to the other one, which is more suitable for the certification process. But that's something that, of course, we can advise you on, and we can discuss together what are the options. We have four spots in the location where we are here, and 3 more in the one Hundborg, 40 kilometers from here. And then, of course, as you all know, data, that's the new hype today, and that's also what you need to make a better product. So we are collecting data every second, and this data get anonymized. So, of course, we need to take care that the information that we provide to you, it's good for you, but it is not affecting the others in testing. And based on that, then you just do your assumptions. We can do the certification process using this data. So we have set up a system which is compliant with the certification, right, Anka? Yes. And then we also would like to support a lot research also from university, educational institutions. So if you are interested in having this data, anonymized of course, then you just get in contact with us, and then you can get them and use them for your simulations and your tests. So yeah, to conclude, basically we know that there are a lot of good ideas outside, and our task is to help developing and helping you to get to the market. The team is quite small but very experienced, and should you need more technical information, then these are the 2 guys that you should contact. And Ankar is here also, so he can answer to the very technical part of this presentation. Yeah, so we hope that that was a little bit of a push for some of you who are testing, for universities with new concepts, to come to Denmark and test your products here. So if there is any question, then now is the moment. Now the Ankar can answer. No, doesn't look like. So then, otherwise, we can move to the following speaker. That's Quentin. Are you there? Yes, I can see you. I think we are a little ahead of schedule, but if you are here, it shouldn't be a problem.
I'm here, okay.
Yeah, perfect. So he's from Voltsys Renewable Energy Solutions from Ireland, and yeah, the floor is yours.
I think you're seeing my screen already.
Yes.
I'm trying to figure out how to get this to be the full screen.
No, that's perfect. Yeah.
Okay. I can't see all of them, but maybe you can. So good morning, yes. Ireland, southwest coast of Ireland, which has similar winds to where you are in Denmark, I'm sure, because we look out on the Atlantic. We originally developed wind turbines, but we quickly moved into just developing controllers. Just a brief potted history of the typical domestic installation. You had a turbine connected to a via safety brake, a short circuit brake, to a wind interface which provided rectification, and this went into wind inverters, which typically were made by either SMA or by Jinlong or by Power One in Italy. And the early models only worked on the basis of having a power curve based on voltage to control the conversion. Obviously, as the turbine speeds up, you need to export more power to the grid, and as it slows down, you need to rapidly ramp that down. If you don't do it rapidly, particularly as the power decreases, then the inverter might be trying to pull 6 kilowatts from a turbine that's only capable of delivering 2. It'll immediately stall the turbine and increase the. So more recently, a frequency-based power curve, which more accurately reflects the speed of the turbine and the amount of power available. So based on the frequency of the AC, the wild AC coming from the turbine, the inverter converted that amount of power and in turn applied that as torque to the shaft of the generator. There's a wind version of the Trio, of the Trio solar inverter, which was also adopted to work with a special controller that took the frequency of the turbine and converted it into a frequency that it fed to the inverter. So the inverter had a power curve which was simply 50 hertz was 0 watts and 150 hertz was 30 kilowatts, and in between was a sliding scale. But the logic for the power curve was in the interface this time, not in the inverter. Now, as time went on, the companies making wind inverters found that their market was primarily solar, and they gradually decreased their support for wind because as solar panels fell in price and wind turbines remained constant at a constant price, solar became a more economical way for most domestic houses to produce their own electricity. But so I forget what year this was. It was about 6 years ago. But suddenly SMA, FEMA or ABB, and Jinlong all stopped making wind versions of their inverters. And the market was in some difficulty to find an alternative that was reliable. In conjunction with ABB, who ran Power One at the time, we developed a controller to operate with their solar version of their inverters. So the power curve now is stored inside a controller made by us, and through Modbus we disabled the MPPT tracking in the inverter, and through Modbus we told the inverter how much power to convert. And we go through that sequence of reading the voltage or the frequency of the turbine, looking at the power table, and sending a message to the inverter times per second, so that the inverter very quickly and rapidly is kept pulling the correct amount of torque from the shaft of the generator and converting that to electricity. We also produced a smaller unit, which includes a rectifier for the 3 kilowatt to 10 kilowatt sort of size of turbines, working into the new FEMA model of inverter, the Uno DM for the single phase and Trio for 3-phase. So the first unit we had is a small power curve controller, which is a little PLC that we make ourselves. And it stores the power curve, which is fed into it by a USB cable from a laptop computer using our own software. It can either read the turbine AC frequency, the wild AC frequency, which is put into these connectors here, or it can read the DC voltage of the turbine, which is taken from the rectifier here. And then it manages the inverter via Modbus, so you have connections here to the Modbus of the inverter. It also has a micro SD card located up here, and it records the revs of the turbine as frequency, the turbine voltage, and the inverter parameters. So in a typical setup where a company had their own rectifier and dump load, they would use this small PLC to control the inverters and to and to manage the power curve. Okay. So then we developed a rectifier controller, because obviously a lot of wind turbine manufacturers didn't make their own rectifiers and dump loads. So the rectifier picks wild AC and converts it to DC and provides smoothing capacitors. And we have various options of smoothing capacitors depending on the number of pole pairs in the generator and the frequency at which it's running. Obviously, a higher frequency generator needs less capacitance than a one with very few poles and its lower RPM. So this rectifier controller also stores the power curve and has a microprocessor that manages the power curve control of the inverter. So again, we override the MPPT tracking in a solar inverter, and based on either frequency or voltage, we control the power curve via Modbus. We also have a variable dump load, which can be either done by pulse width modulation, so it's completely a variable load. So it doesn't cut in with a bang of 530 volts like the old dump loads used to do. Or if you prefer the old hysteresis system, you can do that. But the hysteresis system used to bring in a dump load at 530 volts and switch it off at 430 volts DC. And that causes a lot of ripple on the DC coming into the inverter. We also provide a DC dump load. The board has a backup power logic that simply works a DC dump load speeding during a power cut. So it's got inputs from the turbine over on the right hand side and outputs to the DC to the inverter and the dump load on the left hand side. It also has an anemometer input for data logging and for turbine control. We speak about that a little bit more later on. And it includes a general purpose relay, which can be triggered by either turbine over voltage, turbine over speed, wind speed running too high, and it can operate an external brake system. Sometimes that'll be a linear actuator to change the pitch of the blades. Sometimes it might be a three-phased wild AC dump load or any other. I've seen people use it to operate a disc brake or release a disc. We're also working with hydro and trying to develop a hydro power curve optimization, because hydro also can't work with standard, in many cases, you can't work with standard MPPT tracking in an inverter. The controller also has a Modbus for external monitoring, so it has a micro SD card inside it that data logs once per second, but it can also provide that information via Modbus. And it stores or transmits the RPM of the turbine voltage, the inverter status, including the AC and DC voltage and current, and its fault state. It can also, if an is connected, it can record the wind speed. And quite importantly, it can also detect phase loss of the turbine. That's particularly important if you have a turbine where you're using a frequency-based power curve. If you have a voltage-based power curve and you lose a phase, the voltage will fall and the generator will generally stop, the inverter will generally stop pulling power because the voltage will have fallen by so much. It will have fallen off the power curve, but the frequency might remain the same depending which phase you lost. If you lost the phase that you're measuring, the frequency will fall off and the inverter will stop pulling power. But if you lose frequency that you're not measuring from two phases that you're not measuring from, the turbine will then continue to be loaded by the inverter, and it will cause a lot of vibration and could do damage. So phase loss detection is quite an important feature. It is possible to use the anemometer logging to improve power curves in a very, we've seen some earlier talks about developing power curve and maximizing your power curve. You're optimizing the power curve table to maximize the power harvested from the turbine at various speeds. I have to say that in my experience, a lot of turbine manufacturers haven't done this work, particularly in the Far East, and turbines come in with power curves that are wildly off the mark. Because we record the wind speed alongside the RPM of the turbine and the power produced by the inverter, it enables manufacturers or turbine developers to optimize their power curves in a very crude way, but it's very simple and straightforward. So generally speaking, because they're both on the same time clock, it's quite convenient to have the power conversion and the wind speed data on the same timeline. But I must say that in my experience, there's about 1.5 to 2 second delay between wind speed increasing, being recorded by a cup anemometer, and the RPM of the turbine increasing and more power being available. And so you have to, in a spreadsheet, you have to offset it by 1 to 2 seconds to get them back into line again. But a very simple procedure is to use an experimental power curve, or the power curve that you're given initially, data log across, then try raising the power curve by 10% across the board and see does that improve or reduce the power production at each wind speed. And if it improved it at a high wind speed, you might take another 10% there. If it made it worse at lower speed, you might reduce it by 5% there and bring it back towards where you were. And as I say, rinse and repeat. If you repeat that procedure a number of times, you can optimize the power production from your turbine for various wind speeds. Another thing because we have a pulse width modulated dump load control, on some sites where people want to do very rough testing of an early prototype, they may not have grid available on the site. And using the pulse width modulation on the dump load, you can actually imitate the power curve that you would use for a turbine. So in Excel, for example, if you change the figures here, so if you started at 50 volts and ended at 400 volts and have a 20 ohm resistor, you change the power curve that you're applying to the turbine. And changing those three figures in those three yellow boxes, you can get very close to an approximation of what an inverter would do with a normal power curve based on the power harvested being proportional to the square of the voltage, which quite often it approximates to. It would give a very rough way of assessing that a turbine actually works before you go to the trouble of putting a grid in place and inverters and so on. We work with ABB and FEMA. ABB, this company has been passed from Power One to ABB to FEMA. And the reason we use these inverters is because they can respond very fast to Modbus commands, much faster than any other inverter that we've seen on the market. If anybody knows an inverter that does it faster, I'd be interested to know about it. But we can basically change the power setting from the controller and tell the inverter to change its power harvesting. We can do that 30 times per second. Whereas most solar inverters take about 2 seconds to respond to the Modbus command. We do use other slower Modbus command inverters for hydro and for CHP. Now, in the last year, I don't think I'm out of order to say that the FEMA company experienced financial difficulties in Q1 to Q3 of this year, and to some extent in Q4 of last year. And this resulted in the company was basically in what is the equivalent, as Americans would know, of a Chapter 11 procedure, where it's managing its creditors. But the company has now been taken over by McLaren and Grey Bull of the Formula One motoring fame. And they're now well funded to ensure procurement of components and continue production. So the company is back in production. But we have had a rough year of it with very slow deliveries and long lead times. Lead time on some products being 8 months to a year. New inverter products are also now in development, so we're quite optimistic with the company going forward that it has the backing of McLaren, Big Grey Bull, and it has very good engineering, so we're quite satisfied that it will work as a product range. For off-grid applications, rather than putting the turbine directly into the battery, in an awful lot of older off-grid applications, the turbine was put into a battery, which means that the MPPT tracking for the turbine was not observed. Turbine spun freely until it got to the battery voltage, and then it was locked to that battery voltage and working basically the same way that an asynchronous turbine would work. It was fixed to a fixed speed almost. We maintain the same system as a grid-tied turbine with the normal controller wind interface and the grid tie inverter working into the AC hot out of Victron or other inverter chargers. That requires, when the Victron changes its frequency, it requires the turbine, this inverter here, to respond to frequency shifting. We can do that with our controller. We can either frequency shift, control the inverter output by the frequency shift on the inverter. On the inverter, we can also read the frequency of the grid through Modbus and respond to it by reducing the power converted by the inverter. And to keep the turbine under the same load, we can increase the dump load. So when the frequency goes above 52 Hertz from the grid, it's detected by the inverter, comes to Modbus into our controller. The controller responds by increasing the dump load and decreasing the power converted through the inverter. And right up to the point where it reaches 53 Hertz, and then it switches off the inverter and all the power from the turbine goes into the dump load. And that, of course, can also work over a three-phase system with 3 inverter chargers, working into the AC hot out at the 3 inverter chargers. Okay, just these are some of the screens on our controller software. The options that you have available. You have the histories, the pulse width modulated dump load. In this case, the dump load would start at 400 volts with 0 power, pulling 100% of the load at 500 volts. So at the dump load, you might have a power curve that's operating up to, we say, 360 volts. And at 400 volts, the dump load would gradually come in. At 500 volts, the dump load would be applied 100%. We have a box here for the ohms of the dump load because we also are able to data log the power going through the dump load and see how much power is going through the dump load over a period of time and how many kilowatts it's producing, how many kilowatt hours is produced in the last few seconds. And you can also take it that if you want to start with a bump, you can start that you start with 80 out of 255 of a dump load setting. So the dump load here in this case, because this is set to 80, will come on at 1/3 of full load, and then will gradually increase as it goes between 400 and 500 volts. Now, when the grid is lost, this circuit doesn't work because it requires the grid to power it. But we have a backup power supply that's able to work a smaller processor that keeps the dump load operating in hysteresis, so it comes on at 530 volts and off at 430, and those settings can be set. For the overvoltage, to operate the relay that would control a permanent dump load, you've got overvoltage and overvoltage timeout. So if it goes above 530 volts, you might operate the dump load or the blades or whatever it is that you want to do to break your turbine, and it would cut out after a certain period of time after it's fallen back below this voltage. Similarly, if the turbine overspeeds in this case above 28 Hertz for 25 seconds or above 30 Hertz for 2 seconds, then the relay will apply and it will time out after a certain period of time when the frequency has fallen below the level. The same things for wind speed. If the anemometer meters per second, or the dump load can come on until it goes below 15 meters per second. And you've got an anemometer timeout and an anemometer multiplier. This is to calibrate for whatever brand of anemometer you're using. And you have the normal power curve input that you can put in whatever power curve you're using for your turbine. And this is all the information that's monitored. You can see the time, the state of the auxiliary relay, the wind speed. Peak wind speed might be the peak wind speed in the last 10 seconds, the inverter power currently, and so on, the turbine frequency, the turbine voltage. Obviously the frequency isn't connected here, so it's not reading Hertz, but it is reading turbine voltage, 320 volts, which interestingly is also what the inverter sees the DC voltage as being. Okay. And then there's advanced options for setting the grid. This is power limiting when the grid frequency goes above 50.3 Hertz or 51.5 Hertz. This is to control in an off-grid situation, but there's all sorts of advanced menu settings there that are available. Okay, now that's me out of time. I don't know if I'm early or late finishing there. Anybody got any questions?
Thank you very much. Any question from the audience? Doesn't seem so. So thanks again. That was the last presentation for this event. So I would like to thank everyone to be on board, the speakers to join with very short notice, some of them, and everyone in general to attend also despite the time zones and all the work that everyone has to do, of course. So the idea is that we would like to have a 9th edition and continue this flow of conferences, because we can see that there is a constant interest of people. We see many recurring names coming in every time and many new ones as well. So there is really the big potential to build a community that can help each other in different parts of the world. There will be the proceedings sent out somewhere in the next week, 10 days, depends on how quick we can edit the videos. But the videos as they are now, like they are already on YouTube, so you can just access them. They are not split in individual videos, so you need to navigate through the 7-hour video that it's uploaded. Presentations will also be sent to the addresses that you use for registration. And we will send you also the link for our LinkedIn group. For those who don't know, we have a group for all the people working and interested into small wind and small, medium and distributed wind. And the idea is that, I mean, we are not managing the group, we are not putting so many things for discussion and so, but the idea is that if any of you runs into something that it could be interesting for the community, just put it in there, no problem. Of course, don't spam. I mean, if people start to put a lot of advertisement, then we might kick them out of the group. But for information, there is an event that you could be interested, there is a conference, or we have reached this result, we have this report published, that's something that could be interesting for the whole community. And it also helps us in the moment of finding new speakers for the following year, because of course that's also a way to find new people. Otherwise, as said, the idea now, the wish we have is that next event will still be live streamed, but trying to focus more on having people actually meeting in presence, because the thing that we are missing, of course, it's all the networking part, all the things that happen when the slides are off. And that's, of course, all the knowledge we get from the slides, that's really important. But the real connections are made at dinner, basically. So for those of you who are far away, we will send you out the precise dates, but it will be roughly in this period here. So we'll try to keep them in this period of September so that it can become a yearly event, and then you can have it in your calendar. And our goal is always to try to make it close to the Husum wind or Hamburg wind, so that if someone comes from the United States, for example, then you can combine the two things in one single trip. Otherwise, anyone who has suggestions for speakers, who has anything they would like to present, you're more than welcome to contact us, and so that we can put you in the list. And of course, also those who have nice ideas, who would like to test, as I said before, our doors are always open. So if there is no question, then I would like to thank everyone for joining, and we hope that we can see you numerous also next year. Thanks for coming.
Thank you.
And we can leave the room open if someone wants to talk, to network a bit with someone in the physical audience or in the digital. But we will stop the recording now, so that all what's said now is out of the lines, let's say.